Hi, it's Dr. Frederick. I want to just talk a little bit about populations and samples. This distribution up here represents a population, and we can sample from it. That's not exactly what I wanted. Let's press that. We take 5 samples. I'm going to clear this. Here we're taking an N of 5 out of a population. We sampled 5. What we want to notice, first of all, is that the range of the smallest value to the highest value is always smaller than the range up here. And that makes a lot of sense. We're not likely to routinely get the largest and smallest values out of there. And we can do this for a long time. And what I want you to look at now is the mean of samples. Let's change this value back to 25. And we're going to take 25. Look at the mean every time that we sample. And it's going to be somewhere near to the mean of the population. And it's not always going to be exact, but on average it's going to be pretty close. And we see that when we look at the means down here, and this is the distribution of sample means. If we just keep sampling over and over and over, the mean of the sampling distribution is always going to become very close to the mean of the parent population. So let's do 10,000 at once. Now there's 10,000 samples of 25, and look at this sampling distribution. The sampling distribution is going to have a mean that's exactly the same as the parent population. And what else do we notice? We notice that the standard deviation is much smaller than the standard deviation of the population that it came from. So I'm going to clear these again and just repeat again. We're going to take a sample often just to see if we can estimate what the parent population looks like. And it turns out to be true that if we take the mean, now this one's very close, it's a good predictor of the population mean. And the standard deviation is always going to be smaller. And it turns out that it's smaller systematically in a certain way, such that we could approximate the standard deviation, the range up here, through a simple conversion of using the n minus 1 in our computation instead of n. And then why do we study samples for populations? First of all, the population is far too large for us to study inexpensively. It would take us a lot of time and a lot of money to look at a population, everybody in it. We take samples because of what happens to the sampling mean, the distribution of those means. What happens is that the distribution of means tells us a lot about the parent population, and the standard deviation of the sampling distribution is easily convertible into a value that estimates the parent population. Now we're just interested in some things. Here's a population that's not normally distributed, but nevertheless it still has the same characteristics, that we tend to see the same mean. The range is always going to be smaller. But no matter what the parent population looks like, we're always going to get a normally distributed sampling distribution. And that's why we can use statistical testing, is because we can always expect to see, I'm losing my mouse here for some reason, okay. We always expect to see this in the sampling distribution, which gives us good prediction of unusual findings. And so if we find something that lands outside of what our sampling distribution ought to be, an unusual score, we can reject a null hypothesis. For instance, we have an unexpected score. All right, in summary, real quick, is we use samples to study populations because it's too expensive to do anything else. We know that there are certain ways to sample that are better than others. the mean of a sampling distribution is always going to be very close to the parent population, no matter what the shape of that distribution is. And then we know a lot of things about how to estimate the standard deviation of the parent population from the sample.